So our next speaker is Professor Peter Winterburn. He's currently Professor of Exploration Geochemistry at MDRU, UBC in Vancouver. Peter is one of a kind. He's distinguished himself as an exploration geochemistry in industry for over 25 years. And in the last couple of years, he's now gone back to academia, where he's now having a big impact. He's able to bring his practical experience in exploration to bear and focus on the key questions from a research point of view, and he's going to be telling us about some of that now.
Thank you very much, John. I'll buy you a beer later. I would like to thank my co-authors on this presentation, Ryan Noble and Dave Laurie. I think most people in the room know both of them. Dave Laurie provided most of the red wine in support of putting this presentation together. When I started assembling this presentation, I was faced with a difficult task because I was asked to talk about exploration geochemistry in this decade and where we were going in the future. And I started working on a presentation, looked through everybody else's abstracts and realized that everybody else who was on in front of me was going to be talking about exactly what I was going to be talking about. So I had to rearrange the whole presentation. What I decided to do in the end was to re-deliver Paul Agnew's talk, but do it at twice the speed and backwards. Oops, we're going too fast now. Sorry, thank you very much. So, State of the Nation, as I said, we're going to do Paul's talk backward. This was his last slide, I believe. As a consequence of economic downturn and retrenchments over quite a few bad ones over the last decade, and we've lost quite a lot of geochemists. There's been quite a big knowledge loss. There's been a big loss in experience, and there's a great concern amongst many of the older geochemists that some of the younger research that's been undertaken at the moment is actually reinventing the wheel. We see people recycling old orientation surveys that the answers were found to them a long, long time ago. And it all represents that loss in the center of this diagram of the middle management, you might call it, in industry. And there are real figures to back up this sort of information. If you look at the breakdown of geochemists within the Association of Applied Geochemists, it's the major group of exploration geochemists, you can see that a decade ago we had a fairly reasonable split, with 32% of those people being junior. If we look at that as it stands at the moment, there's only 13% people, geochemists in that group under the age of 40. And in fact, what's really scary is the blue line represents 6%. So only 6% of geochemists are under the age of 30, which is really scary. And then, of course, there's getting very close to 50% of geochemists over the age of 60, which is quite a shock. And that's represented by the fact that over the last couple of years there have been a loss of a great number of really high quality, well-known geochemists who put a phenomenal amount of experience and development into geochemistry. Most recently of those, obviously, is Kurt Kaiser, who passed away last month. That's been replaced to a great deal, not so much by people in industry, but by people doing contract geochemistry. And we now see that we have a large number of independent contractors doing geochemistry. And in fact, a great number of those are actually geochemists in retirement, that 50% we saw earlier on. With contracting comes a whole pile of positives and negatives that we'll get to in a minute. But to show some numbers again, a decade ago, 25% of our industry was occupied by consultants. If we look at that now, 43% of our industry is occupied by consultants. At the same time, you would have noticed the purple wedge for industry also declined down as well, as did the blue wedge for industry, as did the purple wedge for academia. There are very few universities now actually have professional geochemists on their staff producing younger geochemists for the market. Well, independent contractors are brilliant. I mean, they're all sitting over the age of 60, so they should obviously have a great deal of experience. They're often deadline-driven, more deadline-driven than people in industry, because there's always a degree of flexibility when you're working with a company. Some companies regard them as cheaper because they don't have to carry them as costs, and they don't have to carry them in the headcount, which is usually the bigger important number. On the downside of that, one of the big problems with contractors is that there's often no experience transfer. A job gets done, a report gets handed over, and that's it. And there's often no data integration. The geochemist who's doing the contracting job doesn't that often actually sit with the geophysicist and the geologist in the group and compile a integrated data assessment together to do a final selection of targets. Somebody typically takes the report and does their interpretation of the geochemist's interpretation to assist with the final target selection. And then typically there's no post-mortem. There's no attempt to understand why something didn't work when the results didn't produce the expected drill intersections. The report's pushed off onto the side, and we'll find another contractor next time to do the assessment. Of course, I have to be careful not to shoot myself in the foot here, because I do a bit of contracting on the side as well. I would like to think that I'm sitting on the positive side of contracting. Diversity is an interesting one. My wife insisted I put this slide in. Some 15% of geochemists who are registered with the AAG are in fact non-male, and to put it that way. I actually thought that was pretty abysmal. However, I looked at the number of non-male speakers who are presenting at this 3-day conference, and we're actually doing better than the conference is doing in terms of diversity. And there have obviously been a great number of advances in exploration geochemistry over the last decade. Most of those are listed down the slide here. There's a couple more. A great deal of those are to do with analytical instrumentation and analytical capability, rather than pure geochemistry in the strictest sense. I'm not going to talk about any of those. Like Paul yesterday, I'm not going to talk about isotopes because I don't know much about them either. Undercover exploration is my forte. And there are many regions of the world, as we all know, that are buried under, we call it recent cover, but some of it's up to 30 million years old, so it's not that recent. We only have Canada, Australia, and Chile shown in this diagram, but those are 3 of the main areas that are prime exploration targets. There's obviously many others that are also buried. We're going to quickly whip through some of these. I'm not going to talk about Australia because Paul went through Australia yesterday. I find it despairing sometimes how great things are done in geochemistry, some beautiful science at times that seems to get completely missed by industry. Ian Cameron was a very clever fellow who's unfortunately also passed away. He did a great job down in Chile many years ago demonstrating across the Spence deposit and several other deposits the plausibility of seismic pumping as a mechanism to push groundwater up onto the surface. So we don't have to drill a hole to take the groundwater. We can actually pick it up on the surface where it's subsequently evaporated and left as signatures on the surface. It doesn't even have to be seismic pumping, just straightforward porosity collapse by shaking in the nearby mountains will do exactly the same effect. The groundwater gets forced up to the surface. The downside is that very few companies actually took those lessons on board and took it out and applied it. When you wander out into the Atacama Desert, those of you who have, if you have a geomorphological eye as opposed to a geological eye and don't just see gravel as all the rubbish that you don't want to actually have anything to do with, you can start to see structures through the gravels. You can map out those major faults that are sitting in the bedrock underneath because it's a tectonically active area and those faults are coming all the way up through to the gravels on the surface. Some of these scarps are in excess of 4, 5, up to 10 meters high that are subsequently being eroded down through the gravels. And you can see on the far slide on the far left, that's the type of feature that you're looking for. You're looking for where one side has risen against another, and you're now cutting down through that, producing, it's almost like a ripple type effect. One of the obvious strategies with that sort of thing is instead of sticking samples all over the desert, you actually go in and put very short sample lines across the top of those structures, essentially looking for high conductivity with associated metal signatures. Fairly simple task. Anybody who plays around with Google Earth these days, where there's got super high resolution imagery, these images all came off Google Earth. It's no great complexity. It's not like you have to have your own super expensive satellite or aeroplane taking this type of information. It's all sitting there in the public domain. We'll wander across to Canada now, where I have several students working in various areas of Canada. Stu Hamilton gave us a model many years ago of how we might mobilize elements up to the surface. It's one that we debate really strong and hard. There are many problems with the models that were developed and subsequently redeveloped by various other geochemists. The greatest one of those is that in this type of model, the cations, the metals that we would actually be chasing, they would actually be migrating down, not up, because they're always going to be going towards the top of the ore body. The other big problem with this type of model is that I've seen this case far too often now, of where you strip the till off the top of mineralization, and instead of having a nice oxidizing ore body, instead what you have is some beautiful fresh sulfides sitting there showing no evidence or indication of oxidation whatsoever. So this idea of oxidizing things and electrochemically forcing metals up to the surface, that's not going to be happening in this type of situation. That mineralization is pretty well untouched. Okay, some more data from some of my students. This is molybdenum from a target that one of my students has been working on. I can't tell you where it is because, as many of these things are, it's tied down with confidentiality. But there's the black lines are outlying mineralized ore bodies. You can see there that in the center of the figure we have a molybdenum anomaly over a mineralized ore body, and on the far right another very nice molybdenum anomaly sitting off an ore body. This is a glaciated terrain. We're looking at 5 to 20 meters of till. That geochemistry there isn't something that's wandered up from underground. It's something that's been smeared up vertically by the ice scraping across the top of the mineralization. You don't have to dig very deep here to start encountering thousands of grains of fresh chalcopyrite in the till. It's very simple geochemistry. With that molybdenum anomaly comes along copper, bismuth, and silver as well. The trees do a very nice job of it also. This is the vegetation. Black spruce pine needles from all the trees that have been killed off, but directly across the top of the mineralization, likewise, we get a very nice molybdenum anomaly. No copper in the trees because trees don't like copper very much. It tends to kill them. Kill them off. What's interesting is the concentration of copper in these pine needles is as high as it is in the soil. So it's a very good way of putting your molybdenum down on the surface. However, the really exciting part, which was a real eye-opener for somebody who's a skeptic as me about hydrocarbons coming off of mineral deposits, is that we started to see some very interesting hydrocarbon signatures sitting in exactly the same locations above the mineralization. This is one of several hydrocarbons that are poking up, pentadecane. It's a very long chain hydrocarbon. It's not a gas, it's not a liquid. This is actually a waxy type material. You'll see it's given us an anomalous response across the top of the mineralization, and it's also given us an anomalous response directly over a fault which cuts through the mineralization as well. So there is something in the hydrocarbon story. It's not just us in Canada who are seeing those. Ryan Noble produced earlier this year a paper across another target that is extensively studied down at the northern Mittal deposit. It's an ultramafic hosted nickel sulfide, where he's likewise seeing a whole range of hydrocarbons, what we would consider a acceptable level of anomalous response directly above the mineralization. So there is something in the hydrocarbon story, just that many of us don't like the way that the data gets interpreted by proprietary companies. Where do those hydrocarbons come from? My feeling at the moment, and indeed many other people's feeling at the moment, is they're coming through from bugs, from bacteria. We kicked off a project recently trying to make the link between microbiology and the hydrocarbons and the changes in the geochemical and physicochemical signatures on the surface. A very simple experiment. You take a whole pile of till, you blend that with crushed ore to a concentration of around 200 parts per million, and you leave it cooking. And after only, 30 days on the end there, the bacterial populations in the soil substrate are already starting to change. So you're forcing changes in the material at a phenomenally rapid pace. The great thing about studying genomics is that the price of genomics has absolutely plummeted. I wish that many other commodities would not do the same thing. But in fact, the cost that we are now doing this genomic work at is less than the cost of a conventional geochemical analysis. And you can take it even further than that, because you don't have to analyze the whole genome. All you have to do is identify which genes are the ones that are changing in response to the changing conditions related to the presence of mineralization, and get yourself one of these small devices that just pulls out those individual genes, tells you whether that gene is or isn't abundant. This would be a field portable type of technology, so you wander around with one of these along with your field portable XRF as well. Thank you. I slipped this one in between because many people ask me repeatedly when I give presentations why I haven't used all this whole pile of different partial extractions. There's a whole pile of reasons there why I haven't used all these partial extractions. Interestingly enough, we probably have more options now for partial extractions than we ever had in the past. I wouldn't say that's particularly great. A lot of these are poorly characterized, often inappropriately applied. Proprietary digests and interpretations is bad news because you're asking somebody else to do something on your samples for you that you often have a great lack of understanding about exactly what it is supposed to be doing, or indeed how they're interpreting the data. And of course there's no reference materials for proprietary digestions, so how do you check survey to survey that in fact you're getting exactly the same amount of extraction every time? Unfortunately, our own community propagates the application of these. They're very much beloved by the junior market, who do huge surveys and do huge surveys using these techniques, and further propagate the development of those within inside companies. My feeling is that we should be doing all of this in backward. We should be reverse engineering what is in the soil, what's the chemistry in the soil, where is the signature hiding, and then tailor a geochemical extraction to match that location of the geochemical signature. And you always have to be really, really careful with partial extractions. This is some data from some work that we've been doing. Who would have thought deionized water could be different? Deionized water is probably the simplest partial extraction. You can't get simpler than putting deionized water onto a sample and sending it off to a mass spectrometer. Well, there's data from 2 different laboratories for potassium, and we got different. There's a bias by the one laboratory relative to the other laboratory, and it all came down to the fact, once we'd interrogated both laboratories fairly thoroughly, that the 2 laboratories don't do the digestion at the same temperature. And as we know, you pour more energy into a system, you will do more chemistry. Solubility of most compounds increases with increasing temperature. A very small difference like that. How many companies would actually go to the extent of asking a laboratory of the fine details of the chemical extraction so they can ensure that these types of problems aren't going to actually arise? Okay, the Australians wrapped up landscape. 3 minutes. The Australians wrapped up landscape. The Australians wrapped up landscape evolution a long time ago and did a very good job of it. And this is a very quick demonstration of some use of landscape geochemistry in Canada. There's a typical target we would picked from a geophysical survey. A good geochemist would go in and do a superficial mapping exercise to map out the different till materials across the top of there. They would develop themselves a landscape evolution model, understand how the landscape is getting there, because that is subsequently what is going to drive how they make a geochemical survey and how they interpret the results. And indeed, when we look at the geochemical data from that, it does exactly what we would expect it to do. The northern area is a cryotubated soil. That geochemical plume coming off that purple line in the middle there, which is actually a buried kimberlite. That geochemical plume is being pushed up to the surface by cryotubation. The bottom half here is buried under alluvial material and is cryostatic. It's not doing any mixing whatsoever, and we don't get any geochemical anomaly there whatsoever. What's interesting about this data is it's all field portable XRF, and these some of these values are phenomenally low. We're chasing 9 part per million niobium anomalies here using field portable XRF against a 4 ppm background, which is pretty astonishing. 3 slides to go. My feeling is, and I think we tend to overlook this sometimes, is that everything's linked. It all works together in harmony. You can't do exploration geochemistry without ignoring any one of these components because they're all intimately tied together. This started off as a circle, but because they wanted us to do it in wide format, it slowly progressed into a heart, which I thought was quite sweet. But okay, in summary, I would say that our succession in geochemistry is what we call a broken chain. We are lacking that middle management, and we could face ourselves in serious problems in years to come. It always scares me that you speak to many contractors, independent consultants, and they'll tell you that even during the busy times, they are still turning even during the lean times, they are still turning work away because there is more work than they can actually cope with. That points to a serious deficiency in the number of geochemists in industry. I think to a great extent our application of geochemistry outside of the analytical sphere has somewhat stagnated, with the exception of some of the fine presentations this morning. I get mortified by the fact that we don't know enough chemistry in geochemistry. Far too many times companies take the geologist who can tell you that it is the periodic table and can tell you who developed it, and try and turn them into a geochemist, where in fact they're doing geology, not geochemistry. And all they're doing a lot of the time is making empirical observations of which commodity elements have to be poking out on the surface, rather than really understanding how the geochemistry is interacting with the surface and with the mineralization. We need to take a greater holistic approach, looking at the complete system, understanding the landscape evolution, the soil types, etc., to really make the most of geochemistry. And then there's some promising research. I'm not going to point out my own, of course, but there's some promising research being done on trying to push forward the frontiers of geochemistry. I'd like to thank my students. You'll notice there that I'm doing very well in diversity. And of course, Sean Crowe is the microbiologist who works with me on the microbiology project. Thank you very much.